In this video, we're going to talk about how to select a purification technique. And we're going to talk about the data that you need to be able to do that and some of the trial and error that needs to happen as well. So some of the things that you want to consider when you're looking at compounds to separate. One thing to consider is what phases are the compounds in? How do you tell that? Well, look up the melting points and look up the boiling points of the compounds. And you can figure that out. Once you know what phases the compounds are in that you're trying to separate, you can think about the techniques that you've learned in this lab that might be relevant. So if you have a solid and a liquid you're trying to separate, filtration is a great way to go. If you have two solids that you're trying to separate, you have different techniques that you can try. Recrystallization will allow you to separate two solids. Extraction will allow you to separate two solids if you can take those two solids and dissolve them in a solvent to be able to do that. Acid-base extractions could be useful if you have acidic or basic compounds you're trying to separate. And if you can take one of those solids and dissolve it in a liquid, filtration could be a technique that you could use. If you have two liquids, distillation might be a way to go. Extraction could be a way to go. If you take those liquids and dissolve them in liquids that you can use to extract from. And again, acid-base extractions could be useful there as well, depending upon the characteristics of the molecule that you're looking at. In addition to phases, you want to look at the properties of the compounds that you're trying to separate. The first thing that you want to look at is, do you have a strong acid? Do you have a weak acid? Do you have a base? Do you have a neutral organic? If you do, thinking about an acid-base extraction is a really good way to go. And I'll refer you to the video on acid-base extractions for the details there. The other thing that you want to think about is what type of intermolecular forces or interactions are in the molecules that you're trying to separate. You know that a lot of these techniques are based on differential solubilities, or differences in boiling points. Again, the differences in intermolecular forces play a really big role here. So these are the things that I would start with and then come up with a game plan from there. Many times you can come up with more than one game plan, and to figure out which game plan is better, you wouldn't be able to do that unless you're in the lab actually starting to work on these types of characterizations. So let's look at two examples. One example here, what if you had a mixture that was benzoic acid and naphthalene and you were asked to separate those? Well, the first thing that I'd want to know is what phases are these molecules in if I'm at room temperature. So if I look at the melting point of benzoic acid, it's 252 degrees Fahrenheit. If I look at the melting point of naphthalene, it's 176 degrees Fahrenheit. These are both solids. And so there's a lot of ways that you have that you can try to separate solids. And I'm going to go through one here, but you can think of more on your own. So we know they're both solids. What are their chemical characterizations? Well, if I look at benzoic acid, there's this aromatic ring that is rich in induced dipole interactions. So that's one type of interaction that's there. And if I look at the carboxylic acid here, this is a highly acidic group. So this is a strong acid for an organic acid. And that means that it has special characteristics that you can use to separate it. And we'll talk about that in a minute. If we look at naphthalene, this is all hydrophobic, non-polar surface area. These are induced dipole interactions. So again, two solids, you have a number of different ways that you can separate them. The thing that really sticks out here is benzoic acid is a strong acid. And that means if you take benzoic acid and you add a base to it, and you can add a weak base like sodium bicarbonate, NaHCO3, what's going to happen is you pull off the most acidic proton. And so I'm just going to characterize the rest of the molecule as R, but you have C double bond O, O minus, N8 plus. This is an ionic compound. This is now soluble in water. And so because this is now soluble in water and naphthalene is definitely not going to be soluble in water, an acid-base extraction would be a really good way to go here. So what's your separation plan? Your separation plan would first be to find a solvent that's going to dissolve both of these solids, and that's going to take some work. As I looked this up, ethyl acetate is actually an organic solvent that is not soluble in water that will dissolve both of these compounds. So you can take your benzoic acid and your naphthalene, dissolve them in ethyl acetate, and then to ethyl acetate, add an aqueous solution of sodium bicarbonate. And once you've added your aqueous solution of sodium bicarbonate to that solution, you have deprotonated benzoic acid. This now will go into the aqueous phase, and the naphthalene will stay in the organic ethyl acetate phase and separate them out that way. Again, for the details of this, I refer you to the acid-base extraction video. And I would also encourage you to think about other ways that you might separate these two compounds out, because there's definitely more than one way theoretically that would work. Okay, let's look at a second example. Second example, say that you are asked to separate out a mixture of cyclohexane and a mixture of toluene. First thing that I would want to know is what phases are cyclohexane and toluene at room temperature. So if I look at melting points, the melting point of cyclohexane is 6.5 degrees C. The melting point of toluene is 95 degrees C. The boiling point of cyclohexane is 78 degrees C. The boiling point of toluene is 111 degrees C. So these are both liquids. And so the one technique that you probably really want to think about when you have two liquids is thinking about distillation. Okay, so keep that in the back of your mind. Let's think about chemical characterization of these molecules. If we look at cyclohexane, it's nonpolar. There's a whole bunch of hydrophobic surface area there. So we've got induced dipole interactions for cyclohexane. If we look at toluene, again, a whole bunch of hydrophobic nonpolar surface area here. Again, the type of intermolecular forces that you have are induced dipole interactions. So there's not a lot of difference in terms of the types of intermolecular interactions between these two molecules. So in terms of separation plan, go back to thinking about the phases. These are both liquids. There's not anything that really sticks out on one versus the other in terms of their chemical characterizations with intermolecular forces. So thinking about liquids and liquids, you want to think about distillation. And if you look at these compounds, you know that distillation is based on a difference in boiling point. The difference in boiling point here is 33 degrees C. And so you will probably want to try first a simple distillation. It may be that that boiling point's not large enough to completely separate the two compounds. Fractional distillation, which is another type of distillation, may be needed. So in summary, if you're looking to separate types of compounds out, figure out what phases they're in first, because that will tell you sort of the suite of techniques that you have to use. And once you know what phases they're in, look at the chemical composition of the molecules in terms of the intermolecular interactions that they have, and think about what might be possible in terms of separating them out. In particular, is one a strong acid or a weak acid or a base? If so, separating those from a neutral organic is pretty simple.